We are looking at exponential functions now. The objectives are in front of us. So hopefully after today, you'll be able to evaluate exponential functions. You'll be able to graph exponential functions. We'll look at the definition of the number e, and we'll be solving exponential equations. So recall, an exponential function can be written in the form f of x is equal to b raised to the x power, where we have to say b is a real number. Couple stipulations with b. B has to be greater than 0, so it has to be a positive number, can't be 0. B cannot be 1. If b was 1, it wouldn't be exponential, because 1 raised to any power gives us back 1, so it ends up being a horizontal line. And x is our variable. And x can be any real number. So recall, if you have something raised to an exponent, that exponent is telling you how many times you're multiplying that base, in this case, b, by itself. So b to the x would be b times b dot 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 times b, and you're doing this x times. I just want you guys to be aware, because this is something that some students have a struggle with, is with a negative. So if we had, let's say, a negative 2 squared, because of where those parentheses are in this case, this is saying that I'm carrying that negative 2 while I'm squaring it. So this would be negative 2 times negative 2, which is positive 4. Where if we had written it in the following way, negative 2, and that 2 is squared, or negative, and then 2 squared. This is saying basically I have this negative, and I'm squaring 2. And so this is the same thing as negative 2 times 2, which gives us back negative 4. So there's a difference. You need to see if that negative is being carried with that exponent or not. The conditions for exponential functions are the ones that I just wrote up here. Okay, so let's look at the graph of exponential functions. There's 2 different shapes that you're going to get when you're graphing an exponential function, or you could get, depending on your value of b. So if we have y is equal to b raised to the x power, and your value, your base, is greater than 1, when you graph this, you're going to get the following shape. Well, number raised to the 0 power, except for 0 raised to the 0 power, is always 1. So we're going to have a point here at 0, 1. And this function looks like this. So a couple things to notice about the graph where your base is bigger than 1. Notice that we're strictly increasing. Notice that our domain are all real numbers. There's no trouble spots here. Our range. So there's no value of x that we can plug in that would give us back 0 for our y value, or a negative number. So our range are the values, not including 0, but close to 0, to infinity, or y is greater than 0. Notice we have a horizontal asymptote. So as your x value is heading towards negative infinity, your y value is going to 0. So we have a horizontal asymptote at y equals 0. So those are if our base is greater than 1. If you had your base between 0 and 1, then our shape is going to look a little different when we graph this. So if we have y is equal to b to the x, b is between 0 and 1. Again, anything raised to the 0 power that is not 0 is 1. So if we plug in 0 for x, we get back 1 for y. And our graph would look like the following, or just the similar shape. So basically, it looks like a reflection of y equals b to the x across that y-axis. Notice that in this case, this is strictly decreasing. So our function is strictly decreasing. Our domain is still all real numbers. Our range, we're still getting all y values bigger than 0. So 0 not including to infinity. And we still have a horizontal asymptote at y equals 0. So those are what the graphs of exponential functions look like, and you should be kind of familiar of that shape. So now let's look at graphing some of these exponential functions, and let's use some of the tools that we learned earlier in this course with transformations of functions. And so if we were going to look at the following, f is equal to 2, and that 2 is raised to the x plus 2 power. We want to graph the following, determine the domain, the range, and the horizontal asymptotes of our functions. So recall, if we had our function f of x, and this was equal to 2 raised to the x power, if we plugged in some value in to our argument, so if we looked at f of, in this case, we have x plus 2, that plus 2 in here, this shifts our graph the opposite direction than we think, so it's to the left 2 units. Okay, so we had before one particular point, 0, 1, and if I shift that point 0, 1 to the left 2 units, that's affecting my x value, and I now have a point here at 2, 1. So we could plot points if we want. Technically, if I wanted to do more shifts, I should know more points from y equals 2 to the x. So let's just start plotting some points. So let's say that we plugged in, right. Let's say that we plugged in, and I said left 2 units, but I went right 2 units. And I just noticed that as I'm trying to plot in points, I'm getting an error. So let's plug in, let's say 0. Well, we already did that. So let's plug in, let's plug in 1. So we get 2 raised to the 3rd power, which is 8. Actually, let's plug in 0. We didn't do that. So that would be 2 squared, which is 4. If we plugged in -1 for x, -1 plus 2, and the exponent gives me 1. So 2 to the 1st power is 2. So shifting things to the left or the right, that's not affecting the horizontal asymptote. What's going to affect it is if we're moving our graph up or down. So our domain is not being affected. So domain, again, is all real numbers, which we can write as -infinity to infinity. Our range is still the same as y equals b to the x. It's 0, not including to infinity. Our horizontal asymptote is also the same, which is y equals 0. So looking at the next function, we have f is equal to 2 raised to the x power minus 3. And so recall, if we're adding a constant or subtracting a constant outside of that function y equals b to the x, that's going to affect that, moving it up or down. So this -3, this shifts the graph of y equals b to the x. This shifts it down 3 units. Which in our case is 2 raised to the x power. So we're going to have the same general shape. It's just that our asymptote before, which was y equals 0, that's being shifted down 3 units. Let's just make a dotted line, horizontal line at y equals -3, denoting that's where our asymptote is. Well, before we know we had that point at 0, 1. So if I shift that down 3 units, x stays the same, 0, but 1 minus 3 is -2. So I'm going to have a point here at 0, -2. And so I know what the general shape is going to look like. So our domain is still the same. All real numbers, -infinity to infinity. Our range, though, has changed. We're getting really, really close to, but never getting to y equals -3. So we're going from -3, not including, to infinity. Or another way to state that is y is greater than -3. This has affected our horizontal asymptote, and we now have a horizontal asymptote at y equals -3. So looking at the next example, I have y is equal to that negative in front, and then 2 raised to the x power. And so again, that negative is not part of the base. If it was, you would be bouncing back between positive and negative numbers, and that would not be an exponential function. So recall, if we have a negative in front of our y value, that's reflecting our graph across the x-axis. Give myself a little more room. So looking at y equals -2 to the x, that negative, this is a reflection. Of y equals 2 to the x across the x-axis. Our y values are changing signs. So reflecting that across the x-axis does not change where our asymptote is. Our point, though, that was at 0, 1 before, reflecting that across the y-axis is now going to become 0, -1. And if you'd like, we could plot some more points. So if I plugged in 1 for x, I would have -2. If I plugged in 2 for x, well, 2 squared is 4 with a negative out front is -4. If I plugged in -1 for x, we're going to talk about this in a little in a minute, is that if we have a negative exponent, that we can change the sign by taking our base and bringing that down. So 2 to the -1 power is the same thing as 1/2. And so we'll have a -1/2 for this function if we plug in -1. So x is -1, our y value is -1/2. And so our graph looks like the following. So our domain is still the same. We don't have any trouble spots, -infinity to infinity. Our range has changed. So our range now, we're hitting all the y values from -infinity up to, but not including 0. So y is less than 0. Our horizontal asymptote is still the x-axis, which is the line y equals 0. Okay, so let's recall some rules of exponents. So when we're working with exponential terms, the following are equivalent. So if we have the same base, so let's say we had b raised to the x power times b raised to the y power. If it's the same base, then you're adding your exponents. So this is the same thing as b raised to the x plus y power. Which, if we looked at this, for instance, if you had b squared times b cubed, well, b squared, we know this is just b times b. So there's 2 b's. And b cubed is just b times b times b. And if we sum up how many b's we have now, well, we have 2 plus 3, which there's 5 of them. So we can rewrite this as b to the 5th power. If we have b raised to the x power, and then that's raised to the y power, power to power, we multiply our exponents. So this is b raised to the x times y power. Again, we can look at an example and show that that's true. Let's say we had b cubed, and then that is squared. So that squared is saying take what's inside the parentheses, and we're multiplying it by itself 2 times. So there's our squared. And then if we use the rule above, b cubed, that's 3b's multiplied by itself. And b cubed is 3b's. So if we sum those, that gives us b to the 6. And 3 times 2 is 6. If we had the same base and there was division, so let's say b to the x all over b to the y, we take the exponent on top minus the 1 from the bottom. So this is equal to b raised to the x minus y power. Technically, you're just multiplying them out. So for instance, b cubed over b squared, b times b times b, all over b times b. We can start canceling. There's 2 b's in common. That leaves us with a single b, which is the same thing as b raised to 3 minus 2 power, which is b to the first. If we have b raised to the 0 power, this is equal to 1, as long we have to put the stipulation that b does not equal 0. If we have b raised to a negative exponent, so let's say negative x, this would be the same thing as 1 over b raised to the x power. So let's just show that really quickly, those last two properties that I gave you. Let's erase this real quick and show you why that happens. So let's start out with something we know. So let's look at 2 cubed. And so 2 cubed is telling us we're taking 2 and multiplying 2 by itself 3 times. So 2 times 2 is 4 times 2 is 8. So now let's look at 2 squared. Well, 2 squared is 4. Technically, you have 1 less 2. So we are dividing 8 by 2, and we get 4. 2 to the first power, that's 1 less 2. So we're taking the previous answer, divide it by 2, we get back just 2. If I look at 2 to the 0 power, well, that's 1 less 2 than we had above. So divide that by 2. Well, 2 divided by 2 is 1. 2 to the negative 1 power. So we're taking 1, dividing it by 2. And that gives us 1/2. Let's just do one more. 2 to the negative 2 power. So this is dividing 1/2 by 2. So let's just write that up here. So 1/2 divided by 2. So recall when you have division with fractions, you take the first number times the reciprocal of the second number. So the reciprocal of 2 is 1/2. So 1/2 times 1/2 gives us 1/4. Which, if we use that property, 2 to the negative 2 power, we could rewrite this as 1 over 2 squared, which is also 1/4. So here's rules of exponents that are going to be helpful if you remember. Actually, let's look at one other thing. So let's say that we have 2 separate bases. Let's say we have a base b, and let's say that that is multiplied to something base a, and this is raised to an exponent, let's say just x. So basically, I'm taking what's inside that parentheses, b times a, and we're multiplying it out by itself, x times. And so that's the same thing as b raised to the x. We're going to have x b's multiplied together, and a raised to the x power. So those rules are going to help us. when we're solving exponential functions. And so let's look at solving exponential functions. So right now, we're only going to look at exponential functions where we can manipulate the bases to be the same. So this states that if b to the x is equal to b to the y, then we can say that x is equal to y. So this means if we have two exponential terms equal to each other, and we can manipulate those bases to be the same, then we can just set our exponents equal to each other and solve. So looking at the example, we have 2 raised to the 3x minus 2 power is equal to 32. So we're trying to manipulate 32 to have base 2. And so you're thinking to yourself, how can I rewrite 32 to be 2 to some power? Well, I'll just start counting. So 2 times 2 to the first is 2, 2 squared is 4, 2 cubed is 8, 8 times 2 is 16, that's 2 to the fourth. 16 times 2 is 32, so that is 2 to the 5th power. So we can rewrite 32 as 2 to the 5th power. So we just manipulated our bases to be the same, and so now we can use that rule and set our exponents equal to each other. So we have 3x minus 2 is equal to 5. So this is a linear equation. So we think about how we solve linear equations. We're going to isolate our variables. So let's add 2 to both sides of our equation. So we get 3x is equal to 5 plus 2, which is 7. And then we're going to divide both sides here by 3. And so x is equal to 7/3. And so you can always go back and you can check these, right? We can go in wherever we see an x. Let's replace that with 7/3. So we have 2 raised to the 7/3 power. That 7/3 is times the 3 out front minus 2. Is that really equal to 32? Let's simplify the exponent. I notice I have a 3 in the numerator and the denominator, so that's canceling. And so we're left with 7 minus 2 as our exponent. Is this equal to 32? Yeah, 2 raised to the 5th power is 32. So there were some cases when we were solving equations, we had to check because we might get what are called extraneous solutions. So answers or solutions that actually don't work back in the original. Exponential equations, if we do everything correctly, you shouldn't have extraneous solutions. So it's not necessary to check, but doesn't hurt to. So let's look at another example of solving an exponential equation. So the next one in front of us, we have 5 is raised to the x squared minus x power is equal to 5 raised to the negative 6 power. And so our bases are already the same. Our bases are the same, so we can use the rule setting our exponents equal to each other. So now we know that we have x squared minus x is equal to negative 6. So this is a quadratic equation. So solving quadratics, we're going to set this equal to 0. So let's add 6 to both sides. And so then we would factor this if possible. When I wrote this, this should have been a positive 6 over here. Maybe we can change this to make our life easier. So that was a positive 6. we would subtract 6 on both sides. Okay, now let's do it. So let's factor that. So that factors as x minus 3 all times x plus 2. And so we're looking at, when is x minus 3 equal to 0? Well, that's when x is 3. And we're looking at when x plus 2 is equal to 0. And that is when x is equal to negative 2. So technically, if that had been what I originally wrote, 5 raised to the negative 6 power, when we were solving for that quadratic, it was not factorable. So you would have to go and use your quadratic formula to solve. So our next example, we have 4 is raised to the 2x minus 5 power. This is equal to 1/8. So I need to manipulate those bases to be the same in order to use that rule. I know that 4 squared is 16, and so I cannot manipulate base 8 to be 4. But I noticed that 4 and 8, they can be both manipulated to be base 2. So we know that 4 is the same thing as 2 squared. So let's go back in here and let's rewrite 4. So 4 is the same thing as 2 squared. And that is all raised to the 2x minus 5 power. And this is equal to, well, let's look at 8. 8 can be written as 2 cubed. 2 times 2 is 4, 4 times 2 is 8. So let's rewrite this. This is 1 over 2 cubed. They're not identical yet. We want that 2 cubed. We want that 2, base 2, to be in the numerator. So we want to bring this up into the numerator. And so we can do that by changing the sign of the exponent. While we're doing that and bringing down the other piece, recall, power to power is multiplication. And so we're going to take this 2 here. We're going to distribute it to this exponent. So we would have 2 raised to the 2 times 2x is 4x. And 2 times negative 5 is minus 10, is equal to 2 raised to the, bringing that up changes the sign of the exponent, so negative 3 exponent. So we manipulated the bases to be the same here. And so now we can just set our exponents equal to each other. So we have 4x minus 10 is equal to negative 3. Let's isolate x, so adding 10 to both sides. So we have 4x is equal to negative 3 plus 10, or 10 minus 3 is positive 7. Divide by 4, we get x is 7/4. So the next example is similar to the one above, and the fact that we cannot manipulate 16 to be base 1/2, but we can manipulate both of those to be base 2. So we can take our 2 that's down here in the denominator, we can bring it up into the numerator by changing the sign of the exponent. So that would be 2 to the negative 1 power, all raised to the 2x minus 1 power, is equal to, and 16 is the same thing as 2 raised to the 4th power. So now we have the same base. Well, actually, let's first distribute this negative. So this would be 2 raised to the negative 1 times 2x is negative 2x, and negative 1 times negative 1 is plus 1. So raised to the negative 2x plus 1 power is equal to 2 raised to the 4th power. Bases are the same, so let's set the exponents equal to each other. So we have negative 2x plus 1 equals 4. Let's subtract 1 on both sides. I get negative 2x equals 3. divide both sides by -2. So I get x is equal to -3/2. So next example, we have 5 is raised to the x squared plus 8 power is equal to 125 raised to the 2x power. We want to manipulate the bases to be the same. 5 cubed is the same thing as 125. And so let's rewrite this. We have 5 raised to the x squared plus 8 power is equal to 5 cubed. And that is all raised to the 2x power. Power to power is multiplying. So we have 5 is raised to the x squared plus 8 power is equal to 5, which is raised to the 3 times 2x power. 3 times 2x is 6x. Bases are now the same, so we can set our exponents equal to each other. So we have x squared plus 8 is equal to 6x. So let's rewrite this. This is quadratic, so we want everything on one side. Subtracting 6x on both sides, we get x squared minus 6x plus 8 is equal to 0. There are two numbers that multiply to give us a positive 8 and add to give us a -6, which are -4 and -2. So we can factor that as x minus 4 all times x minus 2. Looking at when x minus 4 equals 0, this is when x is 4. And looking at when x minus 2 is 0, this is when x is equal to 2. So we found two solutions that would work and for that exponential equation. So the next problem below, and I'll scroll up in a minute, is 9 raised to the 2x power, all times 27 raised to the x squared power is equal to 3 raised to the -1 power. So we want to manipulate these bases to be the same. We only want one base on that one side, that left-hand side of the equation. I noticed that 9 and 27 both can be manipulated to be base 3. So let's rewrite those both to be base 3. So 9 is the same thing as 3 squared. So we have 3 squared. That is raised to the 2x power times 27. Well, 27 is 3 cubed. And that is raised to the x squared power times 3 to the -1. So let's first rewrite this power to power. You multiply your exponents. So 3 squared raised to the 2x power is the same thing as 3 raised to the 4x power. Again, power to power is multiplying. So we have 3 cubed raised to the x squared power. That's the same thing as 3 raised to the 3 times x squared power. And this is equal to 3 raised to the -1 power. So same base, multiplication. We add our exponents. So that left-hand side where we have 3 raised to the 4x power times 3 raised to the 3x squared power. That's the same thing as 3 raised to the, I'm going to rewrite it in descending order of powers for the exponent. So this is the same thing as 3x squared plus 4x as our exponent equals 3 raised to the -1. So we manipulated both the bases to be the same on both sides of our equation. And so now we can just set our exponents equal to each other by that rule. So we have 3x squared plus 4x equals -1. So let's add 1 to both sides of the equation because this is a quadratic equation and we want to set it equal to 0. And so we get 3x squared plus 4x plus 1 equals 0. We're going to try to factor this if possible. So we can either use the AC method. So 3 times 1, which is 3. We're looking for two numbers that multiply to 3, but would sum to the middle term 4. And that would be 3 and 1. So you're technically rewriting that middle term with those two numbers, and then you're going to factor by grouping. So let's just do that on the side. So 3x squared, 4x, I'm going to rewrite as plus 3x plus 1x, and then plus 1. So factor by grouping the first two terms together and the last two terms and pull out what they have in common. So 3x squared plus 3x, those both have a 3x in common. And so that would leave us with a single x plus 1. So notice that's the same thing over here, x plus 1. And so we're technically factoring just out a 1. I'm going to just write the 1 there. Normally don't. So same thing as 1 times x plus 1. We wanted what was inside the parentheses to be the same, and they are. So we're going to pull out that parentheses, x plus 1, from both of those groupings. And if you do, for the first grouping, you're left with 3x. Plus, for the second grouping, you're left with that positive 1. So we just factored 3x squared plus 4x plus 1 as x plus 1, all times 3x plus 1, equal to 0. We're setting each of those factors equal to 0. So x plus 1 is equal to 0 when x is equal to negative 1. And 3x plus 1 is equal to 0. So if we subtract 1, 3x equals negative 1, divide by 3, x is negative 1/3. Or when x is negative 1/3. So we have two solutions to that equation. X equals negative 1 and x equals negative 1/3. So our next example, we have E. E is just an irrational number, 2.718, and it goes on forever, that decimal, and it never repeats itself. So we have E is raised to the 2x minus 1 power. This is equal to 1 all over E raised to the 3x power. And that fraction is multiplied by E raised to the negative x power, and that's all raised to the 4th power. Okay, so we want to manipulate this, both sides to have just base E. So I noticed that we can bring up this E to the negative 3x into the numerator and change the sign of our exponent. So this would give us E raised to the 2x minus 1 power is equal to E raised to the negative 3x power. Power to power is multiplying. So this would be E raised to the negative x times 4 is negative 4x power. So we have E raised to the 2x minus 1 power. We can simplify the right-hand side still. We have the same base E multiplied together. And so the rule was add our exponents. So we have E raised to the negative 3x plus negative 4x. So that's going to give me a negative 7x. Set our exponents equal to each other. So we have 2x minus 1 equals negative 7x. So let's subtract 2x on both sides, getting all the x's to one side, constant on the other. So we get negative 1 is equal to negative 7x minus 2x is negative 9x. Divide both sides by negative 9. We get positive 1/9. So negative divided by negative is a positive. So one more example using these rules of exponents and the rule that if we can manipulate the bases to be the same, we can set the exponents equal to each other. So the next example we have here, h is equal to 1/2 raised to the x minus 5 power. This is equal to 8 raised to the x power times 2 raised to the x squared power. So notice all those can be, again, manipulated to be base 2. I don't want 1/2, I want base 2. So let's bring that 2 up into our numerator by changing the sign of our exponent. So that's going to be 2 raised to the -1 power. And then that's all raised to the x minus 5 power is equal to, so 8, remember, was 2 cubed. So this is 2 cubed raised to the x power times 2 raised to the x squared power. Power to power is multiplying. So on the left-hand side, we have -1 times x minus 5 as our exponent. So we have 2 raised to the -x plus 5. I'll distribute that negative sign is equal to 2 raised to the 3rd power raised to the x power is the same thing as 2 raised to the 3x power times 2 raised to the x squared power. So we have 2 raised to the -x plus 5 power is equal to, same base multiplying, we add our exponents. So this would be 2 raised to the x squared, and 3x are not like terms, so rewriting it in descending order of power, x squared plus 3x. Manipulated the bases to be the same, so we're going to set our exponents equal to each other and solve. So we have -x plus 5 equals x squared plus 3x. This is a quadratic equation, so we want to set this equal to 0. So let's add x to both sides, and let's subtract 5 on both sides. So doing so, we get 0 is equal to x squared. 3x plus x gives us plus 4x, and then the minus 5. So there are 2 numbers that multiply to give us -5 and would add to give us a +4. And that would be +5 and -1. So that factors as x plus 5 all times x minus 1. Setting each factor equal to 0, x plus 5 is 0 and x is -5, and x minus 1 is 0 and x is 1. Okay, so you just need to get good at manipulating the bases to be the same in order to be able to solve these equations, exponential equations. Not always we can manipulate bases to be the same. So we'll see soon in another section how to do that if bases cannot be manipulated to be the same, how we would solve. So it's really quite interesting, the definition of E. So let me pull that up. So the number E is actually defined as the following. E is equal to the limit as n is going to infinity of the quantity 1 plus 1 over n, and that quantity is raised to the nth power. So basically, as n is getting larger and larger and larger, going off to infinity, we're getting the number E. And so let's look at that. So I am pulling up in front of us Desmos, and I'm going to go in and I'm going to define our function. And we're going to plug in the values for n and see what value E is, that number E is approximately. So if you look at this, we have here f raised to the nth power, or f of n, is equal to 1 plus 1 divided by n. And this whole thing here is raised to the nth power. So that's our function, what we defined it. And we want to go in and we want to start plugging in values. So if we plug in 10, notice we get back 2.5937. Just pull up what I had and what numbers. If I plugged in 50, so F here, right, F of 50, so N is 50, we get 2.691. Okay, so they're similar, but notice the decimals are off a little bit. So let's go a little further. And so going a little further, we're looking at f of 100. So we get 2.704. If we look at f of 500, we get 2.71. Or above, we have 2.70. So we're getting a little bigger or closer together. So f of 1,000, we get 2.716. So two of the decimal places are the same, the 0.71. If we do f of 10,000, notice we get 2.71, so same as above. And then we have an 8. F of 100,000 gives us, again, 2.718. And then f of 1,000,000. Again, we get 2.718 and then 28. So they're almost identical. And actually, I put the same things. So let's up here get rid of one of the zeros. So notice that this is heading towards what looks like to be 2.718. We can continue to grow that n value off to infinity, and we'll see that our number is approximately 2.718 for E. Okay, so that was an introduction of exponential functions. And we'll get into more examples later on in this chapter in our book.